Hi team, we're back. Exponential and logarithmic equations. So we're going to use all the properties and the definitions that we've used for both exponentials and logarithms to solve their equations. Try not to memorize all of these example problems because you may have something slightly different. Focus on your goal. Your goal is to get x by itself. What obstacle is in your way? Is it the fact that x is in an exponent? Is it in a logarithm? And decide what tools do you have to help you reach your goal. So example 1, solve each exponential equation. There's a couple of things that we can do. Since it's an exponential, wouldn't it be nice if they both had the same base of 2? As a matter of fact, we can do that. We can write 2 as x plus 1 and 16 as 2 to the 4th. This is that property that states if the bases are the same and they're set equal to each other, then the exponents must be the same. Please note, there is no algebra. There was no dividing of 2 or canceling of 2 here. To get from here to here, there was no algebra, only observation. So now we have a linear equation. Yay! Subtract 1 from both sides and we get x equals 3. Here's another exponential problem. Again, it would be nice if we can get everything in terms of the same base. We have a base of 3, a base of 9, and a 27. Well, all of those are powers of 3. I don't know how this problem is going to work out, but I recognize that they all have a base 3, so that's something that we try. So what if we wrote that as 3 to the x squared, 9 as 3 squared to the power of x equals, and 27 is 3 cubed. Well, now we have like bases on the left. That's 3x squared divided by 3 to the 2x equals 3 cubed. So we're dividing like bases on the left, so we can subtract our exponents, and we get 3 to the x squared minus 2x, that's our exponent, equals 3 cubed. Look at there. So now we can actually set those exponents equal to each other. We'll do that up here. We can get x squared minus 2x equals 3. We have a quadratic. That means we need to set it equal to 0. X squared minus 2x minus 3 equals 0. See if we can factor it or use the quadratic formula. It is factorable, so we get x minus 3 times x plus 1 equals 0. So x equals either 3 or x equals a negative 1. And both of them work. There's no restriction, but it's always nice to check. We can get 3 to the 3 squared over 9 cubed. So that's 3 to the 9th divided by 9 cubed, which does in fact give us 27. And for the negative 1, we get 3 to the negative 1 squared divided by 9 to the negative 1. Well, negative 1 squared is just a positive 1, so that gives us 9 times 3, which is 27. So they both work. Part C, we have 2 times e to the exponent of x plus 5. All of that quantity minus 1 equals 5. So again, our goal is to get the x by itself. So let's add 1 to both sides. We get 2e to the x plus 5 equals 6. That x is still in the exponent, but we want to get that and its base alone. We divide both sides by 2. We get e to the x plus 5 equals 3. Now we have a problem where we can't get the bases to look alike. This is where our logarithms come in. We have a base e, so it makes sense to use the natural logarithm. So let's take the natural log of the left side of e to the power of x plus 5 equals the natural log of 3. Remember, if you do something to one side, you have to do it to the other. The understood base e of the natural log is the same as the base of our argument. So remember, that equals just the exponent. That's why we chose natural log. We get natural log of 3. And then to get x by itself, we're going to subtract 5 from both sides. So natural log of 3 minus 5. Those parentheses come in handy. to know that that -5 is not part of the argument. Now, this answer is what we call an exact answer. No calculators were used. No calculators were harmed in the making of this video. But if we do an approximation, that means we put it in our calculator and we get x is approximately -3.901. So be sure you follow the instructions on whether they're asking you for the exact answer or an approximation. All right, D is a little bit more complicated. Not only are they not like bases, 2 and 7, I can't make them like bases, and both of them have an exponent of x. I can't solve for x if it remains in the exponent position. So the only tools that we have to move them to the front are logarithms. Since we have two different bases, we'll just use the common log. So let's take the common log of the left, 2 to the x plus 1 equals the common log of the right, which is 7 to the power of x. That allows us to move the exponents to the front. So we get the quantity x plus 1, still in parentheses, times common log 2 equals x times the common log of 7. Now we want the x's together, but I have an x term on the right, which means I need to distribute on the left. So we need to distribute that common log of 2, x times common log of 2 plus 1 times the common log of 2 equals x times the common log of 7. Now we have terms and we can at least get the x term together. So talk yourself through these problems. Let's get those two x's together. So I'm going to subtract the x log 2. I'm actually going to write that so you can see it. Minus x log 2 minus x log 2. So that leaves us with the common log of 2 on the left and x common log of 7 minus x common log of 2. So we got our x terms on one side. We've got our constant log 2 on the left, but we want a single x. Okay? We can't combine the right. They're not like terms. So what can we do on the right to get a single x? It's a GCF. So let's factor out that x. So we get log 2 equals x times common log of 7 minus the common log of 2. And then we can divide both sides. That gives us the common log of 2 divided by common log of 7 minus the common log of 2, which I'll write it over here on the right-hand side. On that bottom, since we're subtracting two different logarithms, we can rewrite it as a division on that bottom for the argument. So that would give us common log of 2 divided by the common log of 7/2. Again, that is our exact answer. Now our last problem, we kind of have the same issue here. We have e to the power of 2x equals e to the x plus 6. Now this one, I wouldn't necessarily expect you to recognize it right off the bat, because it's probably been a while for some of you. Since, what is it, intermediate algebra, I think, for some of you. This can actually be factored. Watch. If I take both of the terms on the right and I subtract them, move them to the left, we get e to the 2x minus e to the x minus 6 equals 0. This is a problem that's in quadratic form. And if you don't remember what that means whatever here is in the middle, this guy is the middle guy squared. So we can use what's called u substitution. We're going to let u equal e to the x, which means u squared would be e to the 2x. Think of it this way, e to the x, if I were to square it, remember you multiply a power to a power, so that's where we get the 2x. So this becomes u squared minus u minus 6 equals 0. Now we can factor it. This would give us a u minus 3 times u plus 2 equals 0. So u equals a positive 3 and u equals a negative 2. A lot easier to work with. You just have to remember to plug back in the EX. So we get e to the x equals 3 and e to the x equals -2. Now we can take the natural log of both sides. So on the left-hand side, we get natural log of e to the x equals the natural log of 3. And again, our bases on the left are the same, e and e, so that leaves us with just an x equals the natural log of 3. There's the exact answer. There's our first one. Our next one is we take natural log of e to the x equals the natural log of -2. We have a problem here. Remember, in our domains, we only take the logarithms of positive numbers. E, no matter what exponent you take it to, will never be negative. So this does not give us a solution. And you can write yourself a note, not in the domain of logs, the -2. So our only answer is x equals the natural log of 3. This is an exact answer. So the other problems were exponential problems. We could tell because the variable were in the exponents and we had to get them out. Now we want to solve logarithmic equations, but remember there are restricted domains in logarithms. So we have to be careful. We might come up with some extra answers. They're called extraneous solutions that don't work. If we can get it down to one logarithm, we can use the swirly-do definition to solve. In A, remember there's an understood base of e. So using the definition, e to the power of 4 equals x. We are done. This is the exact answer. If we want the approximate answer, we can put it in our calculator and we get x is approximately 54.598. Part B, same thing. We have a single logarithm, so we can use the swirly-do definition. X squared equals 64, which means we have to take the square root of both sides. We get x equals technically plus or minus the square root of 64, but remember, x is our base. Square root plus or minus the square root, but our base cannot be negative. So our only solution is x equals 8. And that makes sense. 8 squared gives us 64. Again, single logarithm. We can once again use the definition and rewrite it. 3 squared equals 4x minus 7. So this one happened to give us a linear equation because that 3 squared is just the constant 9. 4x minus 7. Add 7 to both sides. We get 16 equals 4x. And divide both sides by 4. We get x equals 4. Part D, there's an issue because now we have 2 logarithms and we have a 2 on the other side. So we need to get this in terms of one single logarithm by using our properties. Logarithms represent exponents. When do we add exponents? When we multiply. So we have log base 4 of the quantity x plus 6 times the other argument of x, which equals 2. So we can clean up that argument, distribute, and get log base 4 of x squared plus 6x equals 2. Now we have a single logarithm and we can use our definition. 4 squared equals x squared plus 6x. So we've gotten rid of the obstacle of the logarithms. Now we have a quadratic. A 16 equals x squared plus 6x. So remember with a quadratic, we set it equal to 0. We get 0 equals x squared plus 6x minus 16. And see if we can factor it. 8 and 2 look like they would work. So we get x plus 8 times x minus 2, which would give us 2 solutions of x equals -8 and x equals 2. The problem is, where was that x? It only needs to make part of the equation undefined to make the entire equation undefined. For example, log base 4 of -8. Cannot happen. Not in domain. So our only solution is x equals 2. Now we have a problem with two natural logs. What's kind of causing us a little bit of trouble is the 2 in front of the first natural log on the left. So we can rewrite that as the natural log of x squared, move that 2 back to the exponent position, equals natural log of 2x plus 3. Well, we have a base e on the left, a base e on the right. If they're equal to each other, then that means the arguments must be equal to each other. Again, there was no algebra, only an observation. Now we have a quadratic. We're going to set it equal to 0. X squared minus 2x minus 3 equals 0. It is factorable. X minus 3 times x plus 1 equals 0. Looks like we have two solutions for the quadratic, x equals 3 and x equals -1. Now, notice if I only looked at the natural log on the right, natural log of 2 times a -1 plus 3 would give me the natural log of -2 plus 3, which would give me the natural log of 1, which is okay. That's why it's important to check, because if it's negative, it doesn't automatically mean that it's out. However, that's just the right-hand side. The left-hand side was originally 2 natural log of x. This guy doesn't work. So again, not in the domain. It gives us a negative argument. So the only solution is x equals 3. Okay, gang, so that's it. Again, if you have any questions, don't hesitate to contact me. Go to the Math Success Center. You have resources. I believe in you. Way to go. You guys have been working so hard, and I'm so proud. I'll talk to you soon. Bye.